Have you ever stopped to think about the invisible forces that are shaping our world right now? We're going to connect the dots today, from something as simple as why a heavy backpack makes your shoulder aches, all the way up to the incredible spinning fury of a cyclone. And believe it or not, it all starts with one single idea: pressure.
But before we get into that, let me throw a kind of wild question at you. We're living at the bottom of a giant ocean of air that's constantly pushing down on us from every direction. So, could all that pressure actually crush a person? We're going to find out the answer, and it's pretty surprising.
To even begin to answer that, we first need to get a handle on what pressure actually is. And the best way to do that, honestly, is with an experience we've probably all had: that sore shoulder from a poorly designed backpack.
So, picture this. You've got two people, Mega and Pawan. Their backpacks weigh exactly the same, but Mega's bag has these wide, comfy straps, while Pawan's has these skinny little straps that are just digging into his shoulders. Now, why the huge difference in comfort if the weight, the force, is identical?
Well, the answer comes down to one word: pressure. See, the secret isn't just about how much force you're dealing with, but how concentrated that force is. The formula is super simple. Pressure is just the force divided by the area it's pushing on.
And this is where it all clicks into place, right? With Mega's broad strap, that same force gets spread out over a nice, large area. The result? Low pressure. It's totally comfortable. But Pawan's narrow strap takes all that force and focuses it on one tiny little line, creating super high pressure. And that's painful. Same force, totally different pressure.
And once you get this, you start seeing it absolutely everywhere. A nail goes into wood point first because all the force from the hammer is focused on that tiny, tiny tip, creating insane pressure. A knife cuts for the exact same reason. It's all about making the area as small as possible to maximize the pressure.
Okay, so we've got the basics down for solid objects. Now let's take that same exact principle and see how it works with liquids and, the air that's all around us. We're about to scale up from a backpack to the entire planet.
Here's another one of those things you see every day but maybe never think about. Why do we go through all the trouble of putting these massive water tanks way on top of buildings or on their own tall towers? Well, there's a really good reason, and it's all about pressure. This simple experiment explains it all. Imagine you stick a balloon on the end of a pipe. If you only have a little bit of water in there, the balloon barely bulges. But the taller the column of water you pour in, the more the balloon stretches out. It makes sense, right? More height means more water stacked up, which means more weight and way more pressure at the bottom. That's why water tanks are up high, to build up enough pressure to push that water through all the pipes into town.
And if you want to see this on a truly epic scale, just look at a dam. Dams are these incredible feats of engineering because they have to be ridiculously thick at the bottom. Why? Because the pressure from all that water pushing against the base is just immense.
All right, now for the big leap, from water to air. You have to think of our atmosphere as a gigantic ocean of air, miles and miles deep, sitting on top of us, and it creates pressure in the same way. When you stick one of those little rubber suction cups to a wall, you're pushing the air out from underneath it. Then the much higher pressure of the outside air literally pins it to the wall. So, how much pressure are we really talking about? Well, get this. The force of the atmosphere on an area that's just 15 by 15 centimeters, about the size of your hand, is equal to the weight of an object that's 225 kilograms. That's like having 3 adults standing on your hand.
Which brings us right back to that first question: why aren't we all just flattened into pancakes? The answer is balance. The pressure from all the fluids and air inside our bodies is pushing outwards with the exact same force that the atmosphere is pushing inwards. We live in this perfect state of equilibrium. It's pretty amazing.
So this invisible pressure is all around us, in perfect balance. But what happens when that pressure isn't balanced? Well, that's when things start to move. That imbalance is the engine that creates every single gust of wind.
And this leads us to the single most important rule in all of weather. It's super simple. Air will always flow from an area of high pressure to an area of low pressure. Nature is always trying to even things out. It's like a ball rolling downhill.
You've totally felt this at the beach. During the day, the land heats up way faster than the water. That hot air over the land rises, and that creates a low-pressure spot. So what happens? The cooler, high-pressure air over the sea rushes in to fill the gap. That's your sea breeze. And then at night, the whole thing just flips. It's a really cool, elegant little system, and it's all driven by pressure.
Now, a gentle sea breeze is one thing,
But when these pressure differences become really extreme, that simple movement of air can turn incredibly destructive.
This quote from our source material asks a fantastic question. We usually think of wind as pushing things over, right? So how in the world can wind lift a heavy roof straight off a house? The way this works is just fascinating.
Okay, here's the secret, and it's a little bit counterintuitive. High-speed wind moving over a surface actually creates an area of lower air pressure. The faster the air moves, the lower the pressure gets.
So just look at this breakdown. During a big storm, you have super fast wind creating low pressure above the roof. But inside the house, the air is still, so it's at a normal, higher pressure. That difference creates a massive upward force. It's the same principle that makes an airplane wing work, and it can literally lift the roof right off. This is why safety guides sometimes say to open your windows a little. It lets the air flow through and helps even out that pressure difference.
Okay, so now it's time to put it all together. Let's take every concept we've talked about, heating, rising air, low pressure, high-speed winds, and see how they combine to create one of the most powerful forces on Earth, a cyclone. So let's follow the steps. It all kicks off over warm tropical oceans. The sun heats the water, which heats the air right above it. That warm, moist air shoots upwards, leaving behind a huge area of low pressure. Naturally, cooler, high-pressure air from all around rushes in to fill that gap. But, and this is the magic ingredient, because our planet is spinning, that air gets deflected. It starts to rotate. This whole system becomes a self-feeding engine, growing and spinning into that giant, iconic vortex we call a cyclone.
And the result of this enormous pressure engine is just terrifyingly powerful. We're talking wind speeds that can shred buildings, a storm surge, which is basically a wall of ocean water that can be as high as a 3-story building, and rain so heavy it causes catastrophic flooding. And even after the storm passes, the aftermath can be just as bad, affecting everything for weeks.
So there you have it. From a sore shoulder to a spinning superstorm, it's all connected by the simple physics of pressure. Which leaves us with one final thought to chew on. We know that without rotation, air would still rush from high pressure to low. But without the Earth's spin to give it that crucial twist, would the cyclone as we know it even exist? It's a great question that really shows you how all these incredible forces are connected.